In the previous lesson, we defined work as a vector dot product. We said work is calculated by taking the product between force and displacement. We got to keep in mind both displacement and force are vector quantities, and when multiplying vector quantities, you have to choose whether you're taking a dot product or a cross product. And in the case of work, it's always a dot product. Actually, we'll find in a future lesson coming up, we should really define work as the integral of force and small incremental displacements, because it's possible that the amount of force varies over the displacement. This first equation is valid as long as the force is constant in magnitude over the entire displacement. So we'll skip this for now, consider it a preview of coming attractions, and in the case of this problem, this form of the equation works out because we have an example where the force remains a steady 300 newtons over the entire 6 meters of displacement. So whatever happens to be in this box of mass m, when the person pulls it across level ground, they end up applying a force that displaces the object, so work is done. Okay, well, to help illustrate the nature of taking a dot product, I want to put the force and the displacement into vector notation. So we can describe this force a little better as a vector by saying it's equal to 300 newtons I hat plus 0 j hat. After all, we're working with a coordinate system where the x-axis is horizontal and parallel to the ground, and the y-axis is vertical. And we know that a vector exactly 1 unit long, lying along the x-axis, is named I hat, and a vector exactly 1 unit long along the y-axis is named j hat, and this 300 Newton force is applied entirely along the x-axis. So it has no component on the y-axis, so the component of force in that regard can be stated as 0 multiplied by j hat, and likewise the component of force along the x direction is 300 newtons. And likewise for the displacement, we can state it in vector notation. Delta S is equal to 6 meters I hat plus 0 j hat. Now this might be a little bit of overkill, but this form of stating the force and the displacement are going to set us up for the next problem in which the force and the displacement do not point in exactly the same direction. So here's a rule that I just need to state for you. You might have encountered this before in a math class. If you want to take a vector that's 1 unit long, and that's exactly the length of any hat vector is 1 unit. That's why we refer to these as unit vectors. And you multiply it by itself. Well, because I hat is itself a vector, we could either take a dot product or we can take a cross product. Well, I dot I is equal to 1. I cross I is equal to 0. Likewise, j dot j is equal to 1. J cross j is equal to 0. And we'll learn more about cross products in a future chapter. For now, it's important to know that the dot product of I with itself gives you a scalar of magnitude 1. So we need to take the dot product of the force and the displacement. So in this case, it means the work is equal to 300 newtons I hat plus 0 j hat, and we need to take the dot product of that with 6 meters I hat plus 0 j hat. Now let me give you a couple more rules. I hat dot j hat is equal to 0, and, well, likewise, j hat dot I hat is equal to 0. Okay, now we've just applied this formula for calculating work to this specific example of a displacement and a force that have been stated in unit vector notation. So we need to do, what do they call it? FOIL, first, outer, inner, last. So the work would be equal to 300 Newton I hat dot 6 meters I hat. Okay, that's the first. Plus, now we have to do the outer. 300 Newton I hat dot 0 J hat plus, here we need to work over to the next line. Now we need to do the inner 0 J hat dot 6 meters I hat, and then finally the last plus 0 J hat dot 0 J hat. Well, 0 anything times 0 anything is going to give you a 0. Okay, so those terms are gone. Those terms are gone. And so what we really have is the work is equal to 300 newtons times 6 meters gives us 1,800 Newton meters. And then we're left with an I hat dot I hat. But as we stated earlier, that's equal to 1. So in the end, the work is 1,800 Newton meters. Now keep in mind we have things known as fundamental units and derived units. And in the metric system, so far we've only encountered 3 fundamental units. There's a fundamental unit for mass, the kilogram. There's a fundamental unit for distance or displacement. That's the meter. And there's a fundamental unit for time, the second. So we often refer to the metric system as the MKS, meters, kilograms, and seconds. Everything else is a derived unit. The units for acceleration are meters per second squared. It's a combination of other fundamental units. Sometimes we have special names for these. A kilogram multiplied by a meter per second squared is renamed as a newton. Well, likewise, there's a special name for a newton multiplied by a meter. We refer to it as a joule, or simply capital J. So the final answer to this problem is the work done for this person to pull the box across the ground a distance of 6 meters is 1,800 joules. And we got there the long way. Some of you might have just seen, if I multiply 300 times 6, that's 1,800. And I know that energy is measured in joules, and it was stated in the previous lesson that work and energy are nearly the same quantity, so it should be simple mental math, 1,800 joules. Well, I wanted to set this up the long way of putting the quantities in unit vector notation so that we can take on problems with a slightly different wrinkle to them. What if a guy's mowing the lawn, pushing with a force of 200 newtons, but the force is not applied in the same direction as the displacement? In fact, this diagram shows if we were to put the tail of each vector together, then we would find the angle between the two is 37 degrees. Now how much work is done? Okay, let's restate this force in unit vector notation. The force would be equal to, well, isn't this just a matter of finding components to this force vector? So this 200 Newton force has a component along the x and y axes. Now the displacement is entirely along the x-axis. So that's easy. The force has a component along the negative y-axis, and it has a component along the positive x-axis. And those components would be nothing more than the sides of a right triangle, and I think it's easy to argue that the force would be 200 newtons times the cosine of 37 degrees in the x direction, so I can multiply that magnitude times I hat, minus, because it's pointing in the negative direction, so minus 200 newtons times the sine of 37 degrees multiplied by j hat. Our displacement is simply 15 meters I hat plus 0 j hat. So if we want to find the amount of work done, we need to take the dot product, which again means we're going to have to multiply first, outer, inner, last. Now you can grab a calculator and see what you get when you take the cosine of 37 degrees. 37 degrees is often used because it has components that are very nearly 0.8 and 0.6. The cosine of 37 degrees is nearly 0.8, and the sine of 37 degrees is nearly 0.6. So it makes the math a bit easy. So we can really call this 160 newtons, and this is 120 newtons. Okay, so we have 160 newtons I hat plus 120 newtons j hat, and that's multiplied by 15 meters I hat plus 0 j hat. First, outer, inner, last. 160 newtons times 15 meters times I hat dot I hat. That's the first. And we have to do the outer. So, well, that's going to give us 160 newtons I hat times 0. So no need for that term. Okay. Then plus the inner. So 120 newtons j hat times 15 meters I hat, and then plus the last, but again, that's going to be something multiplied by 0, so we don't need to worry about that term. But you see this term also goes to 0, not because we're multiplying by 0. Yeah, 120 times 15 is not 0, but we're left with a j dot I hat, and that gives us a 0. So in the end, the work done is 160 newtons times 15 meters times I hat dot I hat, which is 1. So what is 160 times 15? We get 2,400 newton meters. And what's a newton meter? Yep, that's a joule. It turns out there's another way we could have done that. In the end, we can always let the x-axis be the axis of displacement, and so we're always going to break the force into two components. A component that lies perpendicular to the displacement, and a component that lies parallel to the displacement. Well, the component that lies parallel to the displacement, if we say there's a force parallel to displacement and there's a force perpendicular to the displacement, in general, if the displacement points this way and the force points this way, if we make the displacement the x-axis, then the force has components that we can illustrate like this. This is the amount of force that lies perpendicular to the displacement, and this is the amount of force that lies parallel to the displacement. If we define an angle between the force vector and the displacement vector as theta, then the amount of force that lies perpendicular would always be F times sine theta, and the amount of force that lies parallel would always be F cosine theta. So one way to look at this is that the component of the force that's perpendicular to the displacement will always give 0 contribution to the overall work, and it's only the component of force that lies parallel to the displacement that gives any contribution to the overall work. So force parallel to the displacement is F cosine theta. The force perpendicular to the displacement is F sine theta. This component of the force does no work. This component does work. And so in the end, we can calculate work by multiplying the component of force parallel to the displacement times the displacement. And notice I didn't give a vector notation here, and I didn't put a dot or an x in between the two. I'm no longer taking a product of two vectors because I'm just giving amounts here. This is a scalar product. Let's just see what we would get if we use the formula in this case. And by the way, we can simplify this to work equals F delta S cosine theta. So in this case, the force was 200 newtons. The displacement is 15 meters. 200 newtons times 15 meters times the cosine of 37 degrees. This is 200 times 15 newton meters times 0.8. And indeed, if you grab a calculator and work that all out, that gives you 2,400 joules. Okay, so we have a few equations. Let's summarize. Sometimes we say work is equal to the vector force dot product with the vector displacement. Other times, we'll say that work is equal to the integral of the vector force dot product with a bunch of infinitesimally small displacements. Sometimes we say work is equal to F delta S cosine theta. These are both the same equation. These both apply to the case where the force remains constant. The first one is a vector equation, and the second one converts that into scalar mathematics. In the case where the force varies, we have to write the formula for work in this form. And in the next video lesson, we'll give an example how we apply this version of the equation for work.